segment, the chord, is the segment with endpoints on the circle. Okay. Chords are segments with endpoints on a circle. And then we talked about this on Monday. The most famous chord inside of a circle would automatically be a diameter. Okay. The diameter will always be the longest chord in the circle because if it's a diameter, it's going through the center and touching both sides. It can't be any larger than a diameter, then it would just wind up being outside of the circle and it won't work. Okay. The chords then intercept arcs, which means this chord CD runs into the arc CD. Chords run into arcs. They have what's called an intercepted It's the intercepted arc. It's the arc, think of it this way, it's the arc that's created by that chord. And again, we've done arcs, we've worked with them. We know that measures of arcs are measures of the central angle. So if I drew this in, what are segments AC and AD? Yeah, and what do you know about all the radius in a circle? So that happens. So if I know that I've got those congruent radii, let's say that this angle is 100 degrees. What is arc CD then? Because a couple of weeks ago, excuse me, I went down the wrong way. Excuse me. So a couple of weeks ago, we talked about the idea of arcs and their central angles. The central angle is the measurement of whatever arc it is. The central angle, CAD, has endpoints on the circle, which creates the arc. If I connect those two endpoints, it creates a chord. It starts to get all related back and forth to each other. So what we did is that we knew that arcs and central angles were always the same. And we also knew that let me rephrase that. Which of those two segments or lengths would be longer? The chord length or the arc length? The arc. The arc length would be longer than the chord length. Because if you're walking from point A to point B, if I'm going to walk to that fan, is it shorter for me to walk in a straight line or to walk on a curve to get there? That's why it's that. Okay. So arc lengths is another thing that show up. And again, it's on your formula sheet. But it's one of those things that you guys tend to not fill out correctly. Angle over 360, 2 pi r. And that central angle is the angle at the center of the circle. The sides of that central angle are always the radius. And so on and so on and so on. So like we've said, it's very similar to the things that we've looked at. But what we're going to do is just kind of start to add a couple extra pieces. So far, so good? All right. Now, when you're dealing with arcs, when you're dealing with the relationship with arcs and chords, they also come back and talk about this thing called major and minor arcs. Major and minor arcs are stuff that we defined also a couple weeks ago. And what was the difference between, how would you define major versus minor arc? Major is the bigger one, but it was defined because of the measurements. What did it have to be bigger than? Yeah, it's above 180. It can't go above 360, then you're outside of the circle. Okay. The arc was greater than 180, which means that the minor arc was less than 180. What happens if an arc equals 180? What's that called? It's called a semicircle. Again, the reason why I wanted to make sure we saw this is because in this section and in the preceding sections, you're going to have the language, the lettering, the lingo, and you have to understand the differences. When you're dealing with a major arc, do you remember how many letters they usually use to represent it? 3. It used 3 letters for the major arc. Reason being, guys, please. Reason being is that if I say arc AB, I don't know what direction to go. If I'm given 2 letters, it tells me to go the shortest distance between 2 points. If I say arc ADB, that means I have to go around the other direction. That's why major arcs were generally written with 3 letters. Which meant that minors were 2 letters. Semicircles were, it could have been either or, but I think more often than not they use 3. A lot of times you'll see with semicircles, and you've seen this already in some of the homework and the worksheets and the book work. It'll say segments that appear to be diameters are, which meant that you're creating semicircles. Okay, so that's nothing too crazy. So it just tells you the direction. A DB is longer than AB. So that was just a quick reminder. Also then, you get to the interesting stuff. Now, this is wording. Do you guys agree? Let me do this first before I go to this. Do you guys agree that if you're in one circle, all the radii are the same? You guys okay with that? Now, if you have radii that are the same, and let's say that this central angle is 80 degrees, I could draw another central angle somewhere that's also 80 degrees. You okay with that? Are the radii still the same? Okay. Now, the minute that I do this, what am I creating? I'm creating chords, but I'm also creating not equilateral, isosceles triangles. Okay? The reason why, notice that I've got 2 legs congruent, 2 legs congruent. Are the central angles congruent? How do I show that those 2 triangles are congruent? By what method? Side angle side. I've got 2 sides and the angle in between them. The minute that I have 2 sides and the angle in between them congruent, that means that the 2 triangles are then congruent. So if the 2 triangles are congruent, that means that these 2 have to be congruent because of? Very good. That little corresponding part there. Now the other thing then is, since these 2 chords are the same, that meant these 2 central angles are the same, which means that these arcs are the same. So the long way of saying that is, if you have congruent circles are circles with the same radius, or if you're in the same circle, because then your radius would always be the same. The minute that you have chords that are the same, you have arcs that are the same. Congruent chords mean you have congruent arcs. Because no matter what, this segment, no matter where I place it in the circle, no matter where I place this segment in the circle, it's still going to be the same distance because this is the same and this is still an 80-degree angle. So as it goes around, that segment length will always stay the same. So that's why that segment length being the same will always create this arc measure being the same. Okay? That's where this comes from. And it works going both directions. That's why when it's written out like this, if you have the same circle or in two congruent circles, two minor arcs are congruent if and only if the corresponding chords are congruent. The good old if. Remember what that meant? That meant if and only if, which means you can say it forwards and backwards. If you have corresponding chords are congruent, then you have corresponding arcs congruent. If you have corresponding arcs congruent, then you have chords that are congruent. It works the same way backwards and forwards. If you have a right angle, then you are perpendicular. If you are perpendicular, then you have a right angle. Yes, sir?
Does that say so?
Thorough. Theorem. Abbreviations. Okay? Now, again, as you go through these, are you that cold that you can't write it? Or are you just hiding that you have earphones going? Which is it? So, same idea. It's not that the math or anything here is going to be horrible or scary or bad. You don't have to do any proof stuff at all. But what you're looking at doing is the relationship between the two is generated because we know how to do congruent triangles. And it comes back. It's not, we have to do proofs. You don't have to prove. But the relationship of how all of it comes back together is exactly because of that. Okay? Same thing goes when I'm in here. Those are going to be the same. You get congruent triangles. You get congruent triangles, which means that your central angles are the same, which means that your arcs have to be the same. And that's how all this correlates back and forth. Remember, you have two legs of a triangle that's drawn inside of a circle. If those legs are radii, that means you're always creating at the very least, isosceles triangles. So then if you've got a central angle, then your two base angles will be the same, and so on and so on and so on. That's stuff that shows up. Same thing when you go throwing the math at it. In this case here, it tells you you've got an arc that measures so much, and it's going to ask you to find the arc of the other one. Which means if they happen to be the same, if the chords are the same, what do you know about the arcs? They're the same. So if the arc GH is the same, what's arc IJ?
100.
It's 100. Okay? And again, the reason why all of this works is because that's the same. Those are the same. Since this is given to me, that means this is CPCTC makes this go to here. Oops, too many zeros. Which goes back up to here. Right. You can also get into this even more. I could figure out these two base angles if I wanted. What do each of those base angles have to equal? How much? 40. Be okay with that? You take the 100 out of the 180, what's left? 80. Cut it in half for the both base angles. What's that?
What if one's 39?
It wouldn't work. Then that meant that this chord and this chord weren't the same. Okay? Because you could have the radius being the same. Obviously, you can have the same radius. But if I move this one, let me just draw it again. So if this one's here, and you're saying that what if one of them was 39
and 41.
40? Okay, then these wouldn't be radius. See what I'm saying? Because this would have, if these are both the radius, that means that these have to be the same. Okay, because as you get in it, then it wouldn't work. Now, what I was thinking was if you were drawing, I was thinking of the length of this. So you could, try to get just this piece. If this one was further down here, then you could still have the same radius, but it doesn't necessarily mean that it ran into this angle all the way into here. It could have been a different angle. And that's where things will bounce themselves through. Now, it's kind of a hard thing to draw. Okay. Now, the other thing that'll happen here, this is super easy to see once I get to let me go back to it. When you get into these, since you've got two chords that are the same distance, that means those two chords have to intersect the same amount of arc in the circle. Now, I showed this a second ago. If I took this chord and I moved it around in the circle, it's still gonna run into how many degrees of that circle? It's still gonna run into 100 degrees of that circle, no matter where I place it. Now, since that's always gonna run into 100 degrees of that circle, if I draw in the radius there, wouldn't I just create another congruent set of triangles? Yeah. Now, what that means is, and this is kind of the next little bit of it, is that no matter what happens, the minute you have congruent chords, that means that they have to be equidistant from the center. Congruent chords will always be the same distance from the center of a circle. And the reason that that happens is because, again, CPCTC. Now, when we go back and you start thinking about things that we've drawn, if this is my central angle here, do you guys agree that it's just an isosceles triangle?
Yeah.
Now, if I draw from the central angle to the side opposite me to be perpendicular, what do I automatically do to that because it's isosceles? They bisect it. What do you think happens here then? Yes, sir. Well, I'm sorry, what? CPCTC. Corresponding parts and congruent triangles are congruent. How about this? Just remember how corresponding parts work. All right. Sorry, Joe, go ahead. Yeah. Now, what happens here as you get into this even further, which is one of the next things we look at, as soon as you draw in an isosceles triangle, we know that happens. We know that the base angles are the same because of the rules of isosceles. If I draw in the vertical, it's always going to be perpendicular. And doesn't that make angle, angle, side? Angle, angle, side?
Oh, yeah.
Which means that this distance is the same. And then just like you said a second there, Joe, is that once you get that perpendicular distance, it automatically cuts that other piece in half. So anytime you have a chord, no matter where you take this, wherever you draw this little triangle, if I can make this work. That just means my center of my circle is absolutely nowhere near where I thought it was. I'm just a little bit off on mine. but no matter where you put that other chord that should match up, ish. Wow. Wow, that is not even remotely close to being drawn correctly. Anyway, if you squint just right, you'll see that it fits. So what happens is the two chords, whenever they're placed in the circle, if the chords themselves are, God, that's awful. Just get rid of that. If the chords themselves are congruent, that means that they have to be the same distance from the center. So if the chords are congruent, they're always going to be the same distance from the center.
So basically, this whole lesson is telling us that if the chords are congruent, then the arcs are congruent. If the chords are congruent, then they're equal distance from the center.
Correct. And remember, when you measure distance, do you measure it straight or do you measure it off to the side? Straight. So that's why we say it's perpendicular distance. Yeah, and you're right. That's exactly where all this comes from. I mean, in a roundabout way, he's going nuts. Right? Let's blow bubbles. Come up here. Here. So let's do this. What I want you to do, we're going to solve for x's here, guys. Click that one. Now what you're doing is you're capturing the school. So you want to put a dot here and drag it over. Okay, cover up the whole thing, now let go.
What happened?
It's okay. You bumped it while you're trying to get it. Okay.
Oh, another picture?
Yeah, because you probably didn't make out real well.
I'm done. No.
I think can you grab like on the edge?
I can
At all?
I can try to bend it back like that, like
Use your. You feel better about it now? You got a little bit?
thank you.
No problem. Yeah, you got that one a little screwed up. So again, but also remember, I've used this thing
For a long time.
20 years.
9 years now, at least 9, 10 years, something like that. Now, again, it's a little tough to see, but are these chords, is chord JK and chord ML congruent?
Yeah.
Yes. It says they're both 12. Are they both perpendicular to the center?
Yes, sir.
Which means what do you have to do algebraically? What's that? Some of them are tough when you have the resolutions. It just doesn't show as well. Why they mess around with that a lot is beyond me, but it happens. Yeah. Yes, ma'am. I'm sorry, what? At the 12 and the 11, it was like 12 and 11, then it wouldn't work. You would say no.
I didn't even notice it. I was like, what are those letters there? ML.
But why?
What do you want it about? So this one here, like we were saying, the algebra for these are going to be pretty quick. Guys, one. Now, as you go through one like this, again, very fast two-step algebra. Subtract 3x, add 10. You get 4 again. All right. Now, in theory, you could still take this value and you can then figure out what your radius is. Because what does the segment that goes to the chord do to the chord? Bisects it. So if that means if the whole thing was 12, that means this part would be 6 for here. If I substitute in 4, what's 3 times 4? 12. What's 12 plus 6? 18. So I have a hypotenuse of 18. So that tells me that I get a, I'm sorry, not 18 there. I'm looking at here. Here's my 18. Then I would be able to figure out my radius. What would I do to figure out the radius? Pythagorean theorem. I would do the 18 squared plus 6 squared will equal my radius squared. Well, what would 18 squared be? Press buttons. I knew it ended in a 4. 324 and 36 is 360. Well, that's weird. And then the square root of 360 is. Press the button. On this one here, once you guys get them all done, it probably won't take you more than 12 to 15 minutes tops. Okay? On the whole thing. Okay.
All of it?
On the whole thing. That would be the whole thing, yes. This shouldn't take 12, 15 minutes tops. You just focus, go through it. The math here is really, really, really quick. Okay? We'll go into this a bit further tomorrow. I'm thinking we'll probably go right to the inscribed angles tomorrow. Probably not do the extra day on this stuff, which is not a big deal. And go from there. Yes, ma'am. I don't have videos up. I don't know what the homework is yet. I haven't gotten that far.